Welcome back, everyone, to our masterclass explainer on software engineering. Okay, today we're diving right into section 21.3, and we're looking at why timing acts like a strict law of physics in real-time systems. We often think of software engineering purely in terms of getting the correct output, like just making sure a program calculates the right numbers. But when we transition into embedded real-time systems, it's a whole different ballgame. Suddenly, we are bound by the hard, unforgiving constraints of the physical world. Here is our roadmap for this module. We'll start with an introduction to timing analysis, outline the 3 key timing factors, break down a practical power failure example, scale things up to look at burglar alarms, examine process scheduling, and wrap up with a summary and exam focus. All right, let's jump into section 1, Introduction to Timing Analysis, and talk about the golden rule of real-time systems. I really want you to burn this quote into your memory. In real-time systems, a late answer is a wrong answer. Let's completely shatter a common misconception here. In standard desktop software, if your word processor takes an extra second to run a spell check, it's just a minor annoyance, right? But in real-time embedded systems, time is literally a matter of life and death. Think about an embedded software system controlling a car's braking mechanism. If the system calculates the absolute perfect amount of pressure required to stop the car, but takes 2 seconds too long to send that signal to the brakes, well, a fatal crash still happens. Getting the right answer too late is exactly the same as a total system failure. So, what do we do about it? Well, we rely on timing analysis. This is the absolute core mathematical process we use to guarantee our software behavior lines up perfectly with real-world deadlines. We use this math to calculate precisely how often each concurrent process in our system must execute. It's how we ensure that every single input is processed and all system responses are produced in a timely, predictable way. We are leaving absolutely nothing to chance here. Let's move right along to section 2, 3 key timing factors, which are essentially the pillars of this analysis. Whenever you're analyzing the timing requirements of any embedded real-time system, it all boils down to these 3 foundational pillars for every single process. First, deadlines. This is the absolute time limit to process a stimulus. Second, frequency. This is how many times per second the process must wake up and check for that stimulus, which we often call polling. And third, execution time. This is exactly how long it takes your processor to compute the necessary response once it actually detects the stimulus. Now listen up, because this is a massive exam concept. You absolutely must recognize the difference between average execution time and worst-case execution time. A really common mistake students make is calculating system capacity using the average execution time. But think about it. Execution time fluctuates. You might be waiting on memory or dealing with conditional code branches. In a soft real-time system where a little lag is okay, averages are fine. But in a hard real-time system where failure is catastrophic, no way. You cannot rely on averages. You must base every single calculation on the absolute maximum time a process could possibly take. This is your worst-case execution time. So remember, know your strict deadlines, know your polling frequency, and always calculate based on the worst-case scenario. Let's put this into practice with section 3, the power failure example, stepping into some applied mathematics. We are going to look step by step at a system that detects a mains power drop and has to switch to a battery backup before the attached hardware gets damaged. Now, the laws of physics dictate our deadline. Let's say physical damage occurs at 50 milliseconds. To be safe, we build in a safety margin and set a strict software deadline of 40 milliseconds. Within that tiny 40 millisecond window, the failure must be detected, the software has to run, and the battery must physically spin up and turn on. This breakdown brilliantly illustrates the worst-case scenario for detection. Let's step through it. The system wakes up 250 times a second. That's every 4 milliseconds, just to check the voltage. But to stop false alarms from tiny temporary voltage blips, the system needs 3 consecutive bad readings to actually confirm a failure. 3 checks at 4 milliseconds each takes 12 milliseconds. So what's the absolute worst-case scenario? The worst case is that the power fails a microsecond after a sensor check happens. That means the system sits there for almost a full 4 milliseconds until the next check, plus the 12 milliseconds it needs to confirm. That equals 16 milliseconds just to realize the power is actually gone. Okay, let's do the math to deduce our software window. And this is math you must be able to replicate. We have a 40 millisecond total deadline. We subtract the 16 milliseconds it took to detect the failure. We also happen to know the battery physically takes 16 milliseconds to boot up and provide power. So 40 total, minus 16 to detect, minus 16 for the battery hardware, leaves us with exactly 8 milliseconds. That 8 milliseconds is our worst-case execution time. Your code must execute the battery switch command in 8 milliseconds or less, or the entire system fails. So that's one critical process. But what about scaling up? Let's hit section 4, scaling up, and look at system-level application with burglar alarms. Real-world embedded systems aren't just monitoring one single thing. They are monitoring dozens of stimuli concurrently, and they all have different physical deadlines. For instance, in an alarm system, a power failure demands that rapid 50-millisecond response, but turning on the lights or the audible alarm, that allows a much more relaxed half-second deadline. Activating a voice synthesizer or calling the police could take up to 2 seconds. When you are designing your system, you have to list out these timing constraints for every class of sensor independently. To manage this whole shebang efficiently, engineers group physically adjacent sensors together. Why? Because there's always a trade-off between frequency and execution time. Think about it. If a door alarm must respond within a quarter of a second, you have to check it 4 times per second. If you have 100 sensors, checking them individually 4 times a second means 400 separate process executions every single second. But if you group them by physical proximity, like checking an entire hallway in one single process execution, the execution time for that one check is slightly longer, but you drastically minimize the required polling frequency. It vastly reduces the overall burden on the processor. Once we've crunched those numbers, these process frequencies and execution times are mapped directly onto the system architecture. You can clearly see how the highly critical voltage monitor process runs at 250 Hz with a tiny half-millisecond execution time, while the much more relaxed console display process jogs along at just 50 Hz. Laying it out like this is exactly what allows us to verify, mathematically, that our system can handle the load without missing a beat. But how does the software actually juggle all these competing deadlines at once? That brings us to Section 5, Process Scheduling and Priorities, and the crucial role of the operating system. We have all these concurrent processes needing the CPU at the exact same time. Well, the operating system scheduler steps in. It takes your timing math and assigns CPU processing time based on priority. And where does that priority come from? It's derived directly from our calculated deadlines. The shortest, most critical deadlines, like our power failure, receive the highest priority. They operate at the interrupt level for extremely fast responses. Relaxed deadlines, like polling a door, operate at lower priorities on the clock level. The scheduler guarantees that if a power failure and a door opening happen at the exact same millisecond, the power failure absolutely gets the CPU first. So your math dictates the priority and the OS enforces it. We've covered a ton of ground today. Let's hit Section 6, Summary and Exam Focus for final recap. Remember, timing analysis is literally where software engineering meets the hard laws of physics. For your exams, be absolutely sure you know the 3 pillars: deadlines, frequency, and execution time. You must be able to define worst-case execution time and articulate exactly why we never, ever use average execution time in hard real-time environments. You also need to be totally comfortable explaining the step-by-step math of the power failure scenario we walked through and how the OS scheduler uses those deadlines to assign CPU priority. I'm going to leave you with this final thought to ponder before our next lecture. We know the math works in theory, but how exactly does the bare metal hardware handle all these concurrent priorities without crashing or failing? How does the actual real-time operating system enforce these rules down at a silicon level? Well, we're going to explore exactly how the dispatcher and resource manager pull off that seemingly impossible juggling act in our next module on real-time operating systems. See you then.